Okay, in this video I'm going to talk about Stokes Theorem. Stokes Theorem is a series of space theorems. So the previous talk about the Green Theorem, and this is the second theorem. It's called Stokes Theorem. The last theorem is called Divergence Theorem. So the Green Theorem talks about the relationship between the double integral and the line integral, while the Stokes Theorem talks about the relationship between the surface integral and the line integral. Okay. In the previous lecture, I talked about how to compute the surface integral. Okay. As a matter of fact, also there's a relationship between the surface integral and the line integral. This is what the Stokes theorem is about. Okay, so before talking about that, let me go through the setup of the theorem first before talking about the conclusions. Okay, the Stokes theorem talk about a surface area, a closed surface area given by, let's say for example this figure. So I have a surface represented by delta, and also have a boundaries of this surface, closed surface, which is represented by C. Also, the direction of the surface represented is determined by this way. If we walk along the direction of the boundaries C, and my surface is always on my left hand side. Okay, for example, here is counterclockwise, because if you use a counterclockwise move along that direction, the surface is on my left. Okay. Also, I have a definition of n vector. So n vector is a unit vector that is perpendicular to the tangent plane of the surface at a point. For example, I give you this. Say this is a one point over here. Let's say I have one point here. So that's the black circle represent like the tangent plane. Tangent plane is like the plane only touches the surface at this point. It's called tangent plane. Okay. So for that point, so we can find one line, one vector which is perpendicular to that line, to that tangent vector, a tangent plane, and this unit vector is given by n vector. Okay. The last ingredient before talking about Stokes theorem is vector field. Also, we talk about if I give a vector field represented by the orange color, I can say I have a vector field defined by f, x, y, z. So typically it's given by f1, x, y, z, f2. Oh no, this is a 2, yeah, x, y, and z, and f3, x. This 2 and a 3, x, y, z. So is this defined a vector in 3D space, for example? So after talking about all the ingredients, the Stokes theorem says the integration, the surface integral of this is notation means is a curl of the vector field, the f. Okay, the curl of the vector field f dot product n for any point. This is for any point we can define the curl. This is the n, the unit vector that's perpendicular to that tangent plane on the surface at that point. We compute that dot product. We integrate that over in the entire surface. Okay, it looks a little bit complicated, which is essentially equal to the line integral over the boundary C, okay, of f. This is the same as the f vector defined over here, the vector field, over dr. Of course, I mentioned before, direction is here is counterclockwise, which means if you move along the direction of the C, now the surface is on the left hand side. Okay. Okay. The notation wise, the upside down triangle that's across f. That's the curl of the vector field. This n is the unit vector that's perpendicular to the tangent plane of the surface. In particular, this n is computed by this is a vector divided by the norm itself. This vector is given by partial r u sub v partial u cross product partial r u of v over partial v. So you can imagine here this r is u and v. If I write over here, this is r u and v. This is just the parametric representation of the surface we talked about from the last lecture. So this is represent the surface. Okay, so that's nothing but you compute the partial derivative and compute the cross product. That's it. Okay, I mentioned here this r is the parametric representation of my surface. Okay. Okay, so he already explained C. C is the closed boundary of sigma. The sigma and the direction of the C is defined such that the surface is on the left of C if moving along the direction of C. Okay. So this is the original form of the Stokes theorem. Now, if we compute this one left hand side a little bit, okay, this is if we compute the surface integral in this way, okay, this surface integral, remember from the previous lecture, we talked about how do I write a surface integral into a double integral. So we can rewrite this surface integral into a double integral, assuming that we have a parametric representation of my surface, okay. So we can write down, again here is, I assume we have a parametric representation of this R using V, which is given by X u sub V, Y u sub V, and Z u sub V. And also have U is lower bound by A, a function of V, B, a function of V, and this is V just from C to D. Okay, assuming we have that. Now this one can be written as by following the previous approach I mentioned to compute the surface integral, which can be written as a double integral over the parameters u and v, okay, du and dv, and everything will be the same. The only difference is I have to include this part. This is from the previous lecture. Is partial r u and v time over partial u cross product partial r over partial v cross product computes the norm of that. Okay. Here, this one, if you look at this one, this is the bottom side of this n is just the norm of the whole thing, right? So essentially, this is just my n. It's the same as this over here. So if you do the n time this guy, the norm this guy over here, so this one can be combined as just n, right? So if you time this time n, now it just become n vector, right? So that's why we have n vector over here. So that's why this one is the same as to do the double integration over this is a curl of my vector field dot product the n, which is determined by the partial r over partial u cross product partial r over partial v. Then integrate that over du dv. Okay, that's it. Then this one is essentially equal to a more specific form for that, or a more common use form is this Stokes theorem. It's a double integration over the curl of f time n vector. N vector is partial r over partial u cross product partial r over partial v. The dot product over du dv from this range is just the line integral of f over dr, and the c is defined by the boundaries. Okay, the boundary of the surface. Okay, to understand how this works, I'm going to show you an example how we use this one, this Stokes theorem. Okay. Here, let's see, we consider a surface. So this example I'm going to show you. Here we consider a surface. The surface is given by like the triangle shape. This is for the x-axis you pick a point that is at 1, and for x pick a point at 1, for the y you pick a point at 1. Then you connect these lines. Okay. The surface defined by just x plus y plus z equal to 1. That's a surface. It's a triangle surface. It's given by here is the blue line. And that's defined as f vector. So remember here I have a f field, a vector field over here, right? So the f is given by just z, x, y. Okay. So which means I have here, the first one is f1, x, y, and z. This is f2, x, y, and z, f3, x, y, and z. Okay, so if you look at this one, so we just have for every point you can define a vector associated with that. Also, I define this c. C is defined as the boundaries of this area. So c is the boundary of this area. Okay, associated with this boundary is C1, C2, C3. Also, if the direction defined such that if you move along the direction of this defined direction, then the surface is on my left, so which means it's okay. It satisfies the Stokes theorem. Okay, my question is, okay, I want to use the Stokes theorem to compute the line integral of f over dr. Essentially, I don't want to compute this one directly. I want to use the Stokes theorem because you want to compute this. Of course, I can compute this. You can compute this one as f dr, right? You can compute this as over C1 f dr plus C2 f dr plus C3 f dr. That's okay, but it's a little bit complicated. But we can use the Stokes theorem to compute this. Okay, now I'm going to show you how to use the Stokes theorem to compute this. So basically speaking, first one we still have to, because according to the Stokes theorem, right, this was given by this guy. Okay, this guy. Now, in order to compute this, we have to find a parametric form of my surface sigma. Okay, so step one is we're gonna find a parametric form of my sigma with surface sigma. Okay, so as mentioned in the parametric representation, so the main idea is that, hey, I want to find a point on my surface. Assuming it's on my surface, I want to figure out, hey, how do I represent this point? Okay, so if you give up any point over here, so because any point is satisfy this condition, because this is what the surface defined, x plus y plus z is 1. Okay, so apparently they're not you only have two free variables you can select. For example, if you give you x and y, your z is a determinant basically, right? So naturally I just see for any x, y can freely choose it, and z is just 1 minus x minus y. Yeah, according to this is the problem we have, right? So you start off here, hey, I do have only two variables, x, y. This is 1 minus x, y. If I consider u as x, y, v as y, now I can write this one as u and v, 1 minus u minus v. Okay, we're done. Now here's a question, the one important question is, what is the lower bound and upper bound for u and v? Okay, so as you can imagine, okay, u and v, right, because apparently they must be within 0 and 1. They cannot go greater than 1 because x y plus y plus z is 1, and also each value is non-negative basically, right? So we must have u and v to be within 0 and 1, right? But is this right? Can we just select u from 0 to 1, v from 0 to 1? This is apparently not correct, because if I have u is 0.9, v is 1, for example. If we select u is between 0 and 1, v is between 0 and 1, so I can select this one, right? If we let's pull this point out, u is 0.9, v is 1. Now there's a problem because my v is negative. If I do this u and v, apparently I actually have x, this is equal to x, this is equal to y, which in x is 0.9, y is 1. If you do that one, x plus y is 1.9 already, so your z has to be negative 0.9. Apparently it's not here. So this one, the reason we cannot do this one, because I must make sure that u plus v, since here x plus y plus z is equal to x plus y plus z is equal to 1, I can have x plus y has to be less than equal to 1, greater than 0, right? Which means, because x is u, already defined here, x is u, y is v, so u plus v has to be less than 1, greater than 0, right? Of course, u has to be greater than 0, but has to be less than 1 minus, so u has to be less than 1 minus v. That's why here I have to set this one as 1 minus v. This one has to be 1 minus v. Okay, 1 minus v. Alright. So this is for x, for u. Of course, v has to be 0 and 1, right? Z can move from 0 and 1 freely, okay? So now we have a parametric form, which is u and v, 1 minus u minus v. That's my parametric form. And u is from 0 to 1 minus v. This is indeed set. This is, if you consider this is a v, this is b function of v. Yeah, this is indeed a function of v. It's not freely chosen. It's not just a scalar number, okay? And my v is from 0 to 1, okay? So once we figure out that one, now we're going to have say, hey, I want to compute my the curl and the n is what I have to compute next. Okay. So let's compute what is the n. N is partial r. Apparently r is also here. U and v is what you just put over here is uv 1 minus u minus v. So that's what they have. This is u. Okay, just put all those three numbers together. This is also given by this. Okay, it's partial r over partial u cross product partial r partial v. Okay, given by this. Now partial r partial u, if you consider this is my r. So partial r partial u, first one is 1. Partial r partial u, second one v is not a function of u, so it's 0. And last one is 1 minus u minus v over partial u is negative 1. So partial alpha, partial v, you do the same thing. Is 0, 1, negative 1. Okay. So let's compute the n. N is the just as a cross product, right? Cross product of this one. Let's write over here. So n is partial r, partial u. So I just ignore this unit v. This is a unit v. Okay. Cross partial r unit v over partial v, and this is just already computed it right over here. So according to the cross product definition, you put the ijk as the first row, and then whatever number you have here, put the second row. Whatever number you get over here, put the last row over here. Okay, so which means I put the numbers ijk here, put a 1, negative 1, 0, negative 1 as the second row, 0, 1, negative 1 as last row. Okay. Now when I compute that out, is I, so here use the negative 1. It has to be negative 1, 1 plus 1. Okay, this is just 1, so ignore that one. Then use compute the 2 by 2 matrix over here. So this is 1. So I don't want to go compute the details. It's just how we compute the determinant of a 3 by 3 matrix. So we end up having just I times 1, j plus times 1 plus k times 1. So which is a 1, 1 vector. So this n is down. Okay. So the next one we compute the curl of f. The curl f, so remember f is given by zxy. So curl of f is given by this. The first row is ijk, the second row is partial x, partial y, and z. The last one is partial z. Okay. If you do all the computation stuff out as the same as standard 3 by 3 matrix determinant, so this become I times 1, j times 1, and z times 1. So it's also 1, 1 vector. So both n and the curl is 1, 1, 1. Okay. All right. After doing that, we just can compute this. So according to the Stokes theorem, my line integral is just given by this. Okay. We're just plugging all the stuff we already figured out from the previous step. Step 1, step 2, step 3. So this one is just given by this is okay. So this is integration over c f dr, right? It's just equal to this, right? We just compute this. And we just plug in the range for u and range for v, and the computer will plug in this number, plug in this number. And now we're done, right? So if we do that one, we keep the same value over here. This is the same, okay? And we plug this one as 1, 1, 1. This is 1, 1. So this is a dot product. Remember, this is dot product. The dot product will be entry-wise product in computer sum. So it's 1 times 1 plus 1 times 1 plus 1 times 1, you get 3. And then integrate over there. So this one, again, you do this one by doing 2 steps. The first one, we compute the inner integration, which is integration over u. Okay, the range is already given by here, it's from 0 to 1 minus v. If you do that, you integrate over 3 over u is 3u. 3u integrated as evaluate at 1 minus v and 0. So it's a 3 times 1 minus v minus 3 times 0 is just 3 times 1 minus v. Then you integrate from 0 to 1 over v. Okay, so the integration of 3 over v is this just 3 minus 3v, right? Right? If you do the integration 3 over v is 3v. It's a minus 3v over v is minus 3v squared over 2. Okay, evaluated at 1 and 0. Okay, so when v is 0, you have 3 minus 3 over 2. So when this is when v is 0. So you have this one value. Okay, so it's 3 over, so which is 3 over 2. And minus 1 v 0 is still 0, right? So this is 3 over 2. Okay. So as you can see from here, the Stokes theorem, the main difficult part is we have to sort of figure this n stuff, and this curl is fairly straightforward if we already give you the vector field. So if we go back to the steps we mentioned to use the Stokes theorem, so most time we use Stokes theorem to compute the line integral, because line could be very complicated to compute, but using Stokes theorem can be a little bit easy to figure out. So the main step is we first find the parametric form of this surface, and then we compute this n vector, which is just the partial r uv partial r over partial u cross product partial r partial v. So this is the parametric form of my sigma is my surface. Then we figure out what is my curl of this f given vector field, and finally we compute this is just the double integral. Okay.